So first of all, guys, let's remember again, what is a polynomial? We mentioned many times that the idea is simply multiplication and addition are the operations that we can use. Yes?
Yes,
And so if we arrange those operations based on the number of times the input was used, x is just the input, right? I see, for example, if this is my operation, you can see only addition and multiplication were used. Do you agree? I can rearrange it and say -2 plus 4 times by 1 times by the input plus the input squared plus the input cubed. You understand? That's why polynomials take this form. It's going to be very important. We already mentioned in the last class that the derivative of the constant, a constant is obviously a polynomial because you don't need operations that are more than addition and multiplication. In fact, you don't have any operations at all. Good? The derivative is 0. Remember why? Derivative is 0 because we have a slope of a horizontal line, and that slope is 0. That's what you report, right? When you think of derivative geometrically, just say this. Here is a curve. Look at the curve closely. If it's differentiable at the point where you're looking at, it looks like a straight line near that point. And then report the slope of that straight line. On what, Francis? Is another question on that? On what? We're going to do many examples of derivative. This is just an idea. A horizontal line. But what example? What's the derivative of y equals to 5? What's the derivative? Any line y equals 5 is 0, right? Exactly, right? So you see what it is. So what's the derivative of f of x equal to x, please? Type in the comments. I should see a lot of comments. One person wrote it. Okay, a lot of people begin to write it. That's amazing. That's amazing. Okay, you all understand why the answer is 1 without the need to calculate. Here I actually did the calculation by definition, but it's too obvious. F of x equal to x, that means y equals x. That's a line whose slope I am aware of. The slope of that line is 1. So I report that as my derivative. Good? Now it becomes a little more complicated once I have x squared. There, it's not clear depending on which point you zoom in. You see it's not one line, right? So before we had a horizontal line or a slanted line. The slopes were always the same. Yes? Slopes were always the same. By the way, let me, before moving there, Francis was interested in an example. Let me give this example and ask you to tell me, it's a sort of not example, it's a sort of thinking. Suppose that here is what you found. You found that the derivative of the function at any x is equal to -3, right? And the function itself at 0 equals to 5. I want you to, it's a bit like integration. It's a bit like the next topic, but can you guess what was the original function? You understand what it is saying? When I say f prime of x is -3, I said, right? I said -3, yes. That means what? That means at any x I do the derivative formula for any x, I get the result is -3. I want you to tell me what's the equation or what's an equation of that function. Humira, bullseye. Christiana, nice that you're here. I hope you're feeling good. I worry about you. Come on, guys, only one person answered it. What about the rest? You say you understand it. Great, Tzvi, you got it. Jet, you got it. Great. I hope you're not just copying and pasting from previous comments, but you are correct. Christiana, correct. Guys, okay, so let's understand what's happening here. What does it mean? Look at it, guys. What am I saying when I say the derivative is equal to 5? It means anywhere I zoom in, I see a straight line, and that straight line has the same slope, 5. Remember that I think of curves as consisting of small line segments, microscopic line segments, right? And they are like tiles. They can be all oriented the same way, in which case they form a big line, or they can be kind of changing their orientation. Do you understand what I mean? Yes? Right, so I think of a line. I think of a line as a lot of attached. I mean, there is no space between them. Attached tiles that are oriented the same way. That's just a line curve. Now, another curve is like this, right? Where the line segments are changing orientation. So the fact that I see that the derivative everywhere is 5, that means the slope of each line segment is the same, which means that it forms a line. Now, what line goes through the line has slope -3 and goes through the point 0, 5, right? So what I know is that if I take y minus the point at 0, 5 divided by x minus 0, I get what slope? I get the slope -3, right? So the graph is all xy, exactly, right? All xy that if I measure the slope using those xy, I attain the slope -3, which means y minus 5 equals to -3 times x, which you can write as y equal to -3x plus 5. Easy, right, guys? Easy if you understand what it's about, right? If it's not just pure symbols. Did I show you, I don't remember if I did it in this class, did I show you that question about from what, when, where, about the Stroop test, about, yeah, I think I did. I definitely remember I did. I remember Tzvi's answer. Right, good. If you understand the meaning, it really will affect how you look at the sentence and what the symbols mean. Okay, now we are going to try to find the formula for the derivative when it's f of x equal to x squared. We have done that many times, too many times to bother. So of course you just factor z squared minus x squared, you cancel out z minus x, and you get that the slope is, well, you get that the limit is 2x. Do you understand what 2x means, guys? What is 2x? It means that if I have a graph where the second coordinate is the square of the first coordinate, then the slope at any point that has horizontal coordinate x is twice that horizontal coordinate. You understand what I'm saying, right? I could say the sentence without ever mentioning x if I want to, right? Simply spoken, the slope at any point on the graph, it's twice the horizontal coordinate of the graph. That's what this is saying in terms of geometry. I don't have to say x, it doesn't matter. X is just a letter, it's just a way to express what I just said without x. Clear? Show you what, Francis? Show you what? I mean, you want a picture of quadratic? I can try to show a picture of a quadratic. I don't know what you mean there, but graph. Here is a quadratic, okay? So what do you think will be the slope of the tangent line by 4? You see, here is the point at 4. What would be, you see where the point is? Look at it. This blue point is hovering over 4. Agreed? What's going to be the slope of the tangent line there? 8. It's going to be 8. Exactly, right? So what is it going to be over 6? It's going to be 12. You see that the line gets steeper. So let's say if I zoom in, look at it, I'm zooming in. I'm going to keep 4. I'm going to try to keep 4 in the middle. Okay, here is that line that I see. And if you were to measure the slope over 4, you would see that the slope is essentially 8. You see, 8. Understood? All right. The slope of a quadratic is always twice the horizontal coordinate. That's based on that limit. Now, what about x cubed? How do we find the slope of x cubed? So what we do is we take the derivative formula. When we don't know something, guys, you go to the definition. You understand? Always go to the definition and do your best to extract the necessary information. So how do you look at it? Here is your first problem. How do I factor z cubed minus x cubed divided by z minus x? You don't remember, perhaps? That means you use long division. Here is long division. Do you see that? Long division is something that was a prerequisite for this class. You are supposed to know that. If you do not, you can stay in office hours and we can practice doing that. Okay, so I don't want to spend a long time explaining long division right now. Right? It's just something that you know. You have to have a sense of it. And if you want to, we can talk about why the algorithm works. I mean, a good student can make this, can follow the process, but a very good student understands why it works. And not because they read it somewhere, but because they can reason it out. Okay, always reason out what the idea is about. So by long division, look at it. I want to divide z cubed minus x cubed by z minus x. So how do I obtain z cubed? By what do I multiply z minus x? Obviously by z squared. Now multiply z squared through. It's z cubed minus xz squared. Subtract. What are you left with? You're left with xz squared minus x cubed. So now do the same process. By what do you multiply z to get xz squared? You multiply clearly by xz. And you carry this process, and this is the factor. Look at the factor, guys. It's z minus x, z squared plus xz plus x squared. You see that? Now, what is the pattern if you had to observe it, right? You can try to remember the pattern this way. Look at it. Z cubed minus x cubed is z minus x. And then I write z to a power 1 less than 3. And then z gives its powers 1 by 1 to x. So it's z squared, next it's x, z. And finally, z gives its last power. Look at it. Z to the power of 2, it's x to the power 1, z to the power 1, right? X received 1 power. Z still has a power. Next, it's x squared. I mean, it's written right over here. Do you see that? Yes? Do you see what happens? Z squared, now z to the power of 1, it gave 1 power to x. And finally, z gave its last power, and you have x squared. Have you bothered listening to Oscar Wilde's the Nightingale and the Rose, as I asked? Have you? Yes? You should, guys. Our goal, as somebody said, we are in an academy. And that means we unify ideas. You see, mathematics is not standing by itself. Mathematics should evoke relationship to literature. Literature should evoke relationship to mathematics. So then I push the limit. I will show you in a moment. We'll talk about Nightingale and the roles and why I think of it whenever I do long division. So what happens is we factor out z minus x. We cross it out, and now we can push the limit as z goes to x. What happens here? Look at it. Z squared becomes x squared. X times z becomes x squared and x squared. So we have x squared, x squared, x squared. Altogether, we have 3 of them. So the derivative of a cubic is 3x squared. Do you understand what that means? If I have a cubic function, I need to take the horizontal coordinate, square it, and multiply by 3. Okay? Try to understand it without reference to the x, because if you are focused on the x, you don't recognize that form when another letter is used. You understand? Now, let's try to find the derivative of x to the 4. We're trying to get the pattern. Guys, before I even bother writing the derivative, can you guess what might be the formula? We're trying to develop shortcuts. What do you think will be the derivative of x to the power 4? Type in the comments. Do you have a guess? Okay. Francis, do you mean x cubed over there, like Christiana wrote? Yes, great. Yes, fine. Just to be sure, right? Exactly. Okay, so yes, guys, some of you gave me a guess, and you see that's good. That's exactly what you do. Your guess ends up being correct. Okay, let's see that that we do it first of all by long division, guys. The long division becomes uglier. Look what happens here, guys. Let's try it. We need to understand how to factor differences of 4th powers, right? So z to the 4th minus x to the 4th. Look what happens here. So it's 1 power less than z to the 4. And then look what happens. 3, then 2, then 1, then no z. Z gives its powers 1 by 1, 1 droplet by 1 droplet, until there is no more z. Do you see that? Very easy to remember, correct? Z cubed, x z squared, x squared z. You understand x is gaining powers as z is losing those powers. Do you understand? I'm teaching you how to factor the difference of n powers. And it worries me because, I mean, you might remember this pattern today and forget about the pattern tomorrow. You should always be able to establish it by long division, right? Not to mention, obviously, you should understand why long division works. So, I mean, it should not be a question that, oh, what is long division? So those 2 things you should do, and be able to notice the pattern if you forget it, and then see something that reminds you of it. So you see, so what happens here is I factor out z to the 4 minus x to the 4. Here is that factored form. I can cancel it out. And what happens? I have, this becomes x cubed. This becomes also x cubed, x cubed, x cubed. It becomes 4x cubed. Yes? Let's see if you notice the pattern, guys. First, I want you to tell me, it's a bit annoying to type, but do your best. Tell me, please, what would be the factor form? So x powers, Francis, grow, correct, right? So remember what I just said. So if you have z cubed minus x cubed, what's the pattern? The pattern of factoring it, it's z minus x. Let's even begin with x squared, right? Let's begin with x squared. So if it's x squared, look what really is happening. Z squared minus x squared. So it's z minus x, and then z to 1 power. It only has 1 power to give to x, so it's z plus x. Yes? Now, if it's z cubed minus x cubed, this is z minus x. Now z has z is power 2. Now look at it. Next, it gives 1 power to x, so it's x z to the power 1 plus x squared. There is no more z. Right? If it's z to the 4 minus x to the 4, what's the pattern? The pattern ends up being z minus x. Z cubed plus x z squared. Do you see what happens? x is gaining 1 power as z is losing that power. Z is giving away, drop by drop, everything it has. Okay, do you see how I did it, guys? Now your turn. You tell me. So it always gives the Christiana, I have to be, yes, so it's z to the power of n minus 1 in general. I want you to tell me, what do you think is the situation when it's 5? Write it out in the text. I mean, it's a bit annoying, but do your best. It is easier than binomial expansion, Humira. I can teach binomial expansion, which I do for probability students, but this one is easier. Okay, Christiana. You skipped a term. You have, it's not a big deal, but you see you have xz cubed and then suddenly x cubed z. Very good, Robert. Looks good. Yes, Francis, good. All right, guys, so I think you understand the pattern. This is z minus x, and this is z to the power of 4 plus xz cubed plus x squared z squared plus x cubed z plus x to the power of 4. You understand? So that is this the situation. Now, what is really happening here, guys, right? You might be kind of indifferent about z giving its powers, but if you read or listen to that story, Nightingale and the Rose, would you tell me, please, who here is the Nightingale and who here is the Rose in the difference of 5 powers, in the difference of 3 powers? Who is the Nightingale and who is the Rose? Exactly, Francis. What do I mean? Here, Robert understands. The Nightingale is Z and the Rose is X. So Robert understands it pretty good, what I mean. Yes? Z, the Nightingale, is giving its blood 1 droplet after 1 droplet until it is gone. But let me tell you who is the real Nightingale. The real Nightingale is me, because I am bleeding here for you, right? Indifferent, callous strangers who don't bother learning the math that I'm trying to teach you. 1 droplet at a time. And if you read that book or look at the story, what happens at the end? It was completely in vain, for no point. This is z to the n minus x to the n. What's the general pattern there? It is z minus x, z to the n minus 1, as Christiana said, plus x z to the n minus 2, plus x squared z to the n minus 3, so on until there is no more z. Right? Now, how many terms are added here? How many terms? We see if it's n, how many terms am I adding here? Well, you know how we can count? We can count rather simply, because you see that there is x, that's 1. We can use the power 2 all the way to here, n minus 1, right? So there are n minus 1 copies of x, so we have n minus 1 additions and 1 extra addition, this one. So altogether 1 plus n minus 1 additions, or n terms that are added together. You follow? You all see that, guys, right? Not just 3 people, not just 4 people, but all of you see that, I hope, or very, very many of you see it. Yeah, I know, Humira, you see it, but what about the people that don't participate? What about Miriam? What about Marva? What about Vildan? Do you see that? Good. You will see, Francis, right? You will see. You can look at the exams that we have before. Okay. So, guys, here is the expansion for z to the 6 minus x to the 6. As always, of course, just recognizing the pattern, you might worry. By the way, I mean, it seems that people are disappearing. I mean, I have one. How many people are here? Come on, guys. Turn your cameras on, please, so that I could say, Marva, maybe you can turn your camera on. Maybe, well, Humira participates, so I don't know, but Ling Sing, maybe you can turn your camera on. Angelo, I don't see you today. Okay. Who else? Brianna, consider that. Good. On. Barbara, I want to see what you are like. Great, great. Thank you, guys. Now, this is the pattern that we're going to try to verify it's truly holding, right? How do we do that? Look at it, guys. How do I know that? Because I don't want to do long division forever, right? I can do it for power 3, for power 4, if I really have to, for power 5, but I'll tire. And I recognize the pattern. I want to prove the pattern holds. No worries, Barbara, right? Sorry that I pick. Again, guys, I am always in between two things. I don't like forcing you to turn the camera on. I also don't like when that is usurped, that I am not invasive. Good? People sometimes take advantage of my seemingly good nature, but I'm a beast when it comes to grading, so don't try me. Here is the question, guys. So I want to prove that that indeed z to the n minus z minus x to the n is z minus x, z to the n minus 1 plus x z n minus 2 plus all the way to x to the power of n minus 1, right? How do I verify this is true? This is what I can do, guys. Look at it. I'm going to label this expression. I'll call it S. Sum is S, okay? This is my S. So S multiplied by Z, look at it. S multiplied by Z becomes Z to the N plus X Z to the N minus 1 plus X squared Z to the N minus 2 all the way to plus X to the N minus 2 Z squared plus X to the N minus 1 Z. If I multiply S by Z. Why do we need to prove it, Francis? To know that it's true, because maybe the pattern fails to hold, right? You will see, you always, guys, if you do mathematics, you're obsessive about proofs, right? You cannot stand anything that's not proven. Because, you know, I mean, what did I watch today? I mean, you see, I could show you. It's very interesting what happened during the witch trials. You see, so I was watching the German witch trials and how they were proving that a person is a witch. And I think, well, here you go, right? That's what happens when people don't understand how to prove things and don't understand the meaning of rigor or the meaning of proof or the meaning of argument, right? So it makes people very dark. So here we take s and we multiply s by x. And what do we get then? Then we have x z to the n minus 1. This is s here, remember that? Plus x squared z to the n minus 2 plus here we have x n minus 1 z plus x to the power of n. And then when I subtract, let's see what happens here, guys, when I subtract. When I subtract, look what I have. This term cancels, so the second term of the top line cancels the first term of the bottom line, right? Now, same thing happens here. We have cancellations all the way to what? Look at it. This is canceled. This term will be canceled by something that would be here. So everything is canceled except for what? What remains here is z to the n. This is what remains. And this is what remains. So the result is z to the n minus x to the n. So what I have here, if I simplify here, this is zs minus xs. And so I have that z minus x multiplied by s multiplied by that equals to z to the n minus x to the n, which means my pattern that I picked up always holds. You understand what I verified? I hope, guys, you understood that I first know how to get to that pattern. I can use long division to notice the pattern, but once I notice the pattern, I must ensure that it always holds. And this is one easy way to do so. So I know that my factorization is absolutely correct. Now, this gives us the ability to prove that the derivative of x to the n is nx to the n minus 1. Here we go. We are taking x to the n, we take the derivative, limit as z goes to x, f of z minus f of x over z minus x. Yes? We factor the numerator. We write it as z minus x, and we have that formula. We cancel it out. We already counted, you see? Look what happens. We're taking the limit of this summation. Now, the sum of the powers of x plus the powers of z is n minus 1. You see, only the z become x. How many total? We have 1 all the way to n minus 1. So n minus 1 sums from here, and then 1 extra sum here. So we have n summations of x to the n minus 1, thereby giving us the first formula. That's the power rule. We now have a shortcut, guys. First shortcut where we don't need to go through the process of the derivative. I right away now know that the derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the 7 is 7x to the 6. Do you understand? I derived it. I did this calculation once, and if I have to, I recall it in general, but I can now move faster. I don't have to stop. Yes, I don't have to stop. Isn't it amazing? Here is what happens. You see that, guys? We figured out how to take those derivatives. Now, we are going to learn some further shortcuts. Let's try to see what you imagine those to be before I even explain them. Let's see if you can guess, guys. If I asked you, and you can do it fast, if I asked you to take the derivative of, let's say, 10x squared minus 3x cubed, you will tell me the derivative is what? In fact, let me just change it slightly, okay? Will you allow me to make the slight modification before I ask you? So let's say plus 10, okay? And you take the derivative of that. Tell me what you think will be the answer very fast. Okay, Francis is there. Okay, great. Great. We already have 4 people responding. More. Come on, guys. Show me that you are here. Okay, Mariam, good. Brianna, let's see what you would say about it. Okay. So the answer is, as you guessed correctly, the answer is 20x minus 9x squared. Yes? So the guess is absolutely correct. That's amazing. Good. Now, guys, what about if I ask you to find, let's say, the derivative of 10x squared divided by 3x cubed minus 7? What would you have written? Just checking what you would say. So the rule, Francis, you did something there, right? Okay, Miriam. Okay, so let's see if more people would say something there. Robert wrote something. And again, guys, my God, are you magically disappearing? Anna. Okay, so a lot of you wrote this, guys. A lot of you wrote 20x divided by 9x squared. Yes? Yes? And here you will be absolutely and terribly wrong. It's not right. That's okay. We're just learning. My point, of course, guys, that if you decide to memorize, you will make many mistakes. You will lose your way. I guarantee it. Okay. So even if nothing interests you except for the grade, the best way to it is actually to be interested in it and to actually understand it. Right? There is either you face the choice. Either you memorize 500 pages or you understand one. All of calculus, I think, to me, it's one page. Okay, but it needs to be understood. The other alternative is memorize 500 pages and every single question is new to you. And after 500 pages, I add one more page and you don't know how to do it. And you cannot use it ever. Well, it's for many reasons. We need to establish the rules, okay? So that's our goal. We are establishing as many shortcuts as we possibly can, and we shall see. Okay, guys, so here are some rules. Do you see that first rule is that the derivative of a constant times a function is constant times the derivative of the function. That's rule number one. Rule number two is that the derivative of a sum is always the sum of the derivative. Elizabeth, what was nonsense, Elizabeth? I didn't see what you wrote. I mean, not Elizabeth, I mean Gabby. I'm now curious. Go there. Okay, guys, are you there? Ah, no worries. So, guys, here is how we go about it, right? So it's about pattern recognition. Do you understand what I imagine doing, right? So what is the question? What is this? C times f of x, right? I know now how to take the derivative of x squared, right? That's just 2x based on the power rule shortcut that we hopefully established. Yes, factor it out, do this limit, it's 2x. But what is the derivative of 5x squared, right? This process tells us that we can factor the 5 and just take the derivative of x squared. That's why your guess was correct. It's kind of almost tempting to do it, you see? That's the first property. Now, why is that true? Let's look at it, guys. Very simply, when I apply the definition of the derivative to a constant times the function, I get this limit. Do you agree? This is just some function. So this is the function at z minus the function at x. And what can I do? Look at it. I can factor out the constant. And what do I see here? When I see this fraction, I recognize that in the limit, it will be the derivative of this f is my x squared, so to speak, right? It's a function that I know how to differentiate. And the c is just modify that function by a scalar, right? Start with x squared and multiply it by 7. You understand? So when in the definition, I will see the definition of the derivative of the x squared of the original function. So that's what it tells me. Take the derivative of the function, skip over the constant. Let's just, let me try to confuse you for a moment, if you're not confused enough already. Guys, didn't I just say that the derivative of a constant? Didn't I say that the derivative of a constant equals 0? That's correct, right? Derivative of a constant is 0. So isn't the derivative of a constant times the function? There is a constant here. Why shouldn't that be 0? The derivative of the constant is 0. Why is that not happening? Right? I just said before, derivative of 5 is 0. So why is the derivative of a constant times the function not 0? Why do I suddenly skip over the constant? Well, why is that not 0? I mean, maybe the question, of course, is a bit ridiculous. If you understand the definition, I mean, why should it be 0? Does it stump you guys before I move on, or it completely the objection makes no sense whatsoever to you? Yes, what? Yes stumps, or yes makes no sense whatsoever, the objection? Derivative of a constant is 0. Okay, Zakaria says something, f of x isn't, well, that's something else. You're talking about product rule, Zakaria. That's still something else. I'm asking something simpler before product rule. Right, one person is caught by it, guys, right? Derivative of a constant is 0. Why derivative of a constant times a function not 0? Why are you stumped? All right. Because the constant is tied to a function. That's something like that, right? But even simpler, guys, why is the derivative of a constant 0? Because when you say constant, you're saying a function that generates a horizontal line. If you take 5 and multiply by x squared, does that look like it will have slope 0? 5 times x, right? The derivative of 5 is 0, but 5 times x, it's a line that has slope 5, right? So it should be an objection that makes no sense to you whatsoever. What's there to object? Right? I mean, you understand? I mean, why is the derivative of a constant 0? It's because we get a horizontal line. Constant times a function is usually not a horizontal line because the function is not going to, if the function is x squared, 5 times x squared does not look like a horizontal line. Obviously, it should not be 0. The only time you get derivative equal to 0 is if the graph is a horizontal line. Do you agree? If the derivative everywhere is 0, it can only be a horizontal line. Is that clear to you geometrically? Right, so confusion is, I mean, you understand what my point is, guys. You can be confused by a billion things. Like there is not enough people in the world to explain all your confusions, right? If you don't understand something, then every left, every right, everything is, I mean, there's not enough explanation, no amount of information that will clear it away. right? So this objection is completely nonsensical. It's meaningless. I mean, I say to me, I mean, I would be puzzled. Maybe that's what you're puzzled by. What are you talking about, right? How can you even come up to such a ridiculous conclusion that the derivative of a constant times a function is 0, right? It just would not even occur to me to come up. Like, you see, you understand? Like you have a fork, right? It will not occur to me to stab myself in the eye with it. In general, right? So there are many things that will not occur to me in how a person can use a fork, right? You understand what I mean, right? So anything, right? There's just yes. So I hope you understand. Yes, exactly. If fx were another constant, then a constant times a constant will be just whatever other number, and that means some horizontal line. Understand? So the derivative is 0 if and only if it's a horizontal line, and we've established that. Why can't what? You see, Francis, you say the word eat, but the word eat is very vague. Eat what? Why can't what be 0? It can be 0. Look at it. So suppose that f of x equal to 7 and the constant is equal to 2. Then c times f of x is equal to 2 times 7, which is 14. And then the derivative of that is 0. Right? But it's still true that it's the derivative of a constant times the derivative of the function, because that would be constant times 0. So this theorem is true always. Right? But the derivative of a constant times a function is only 0 if that function itself is constant. You understand? Or the c is 0. If c is 0, it will obviously make it 0. Agree? But that's true with the formula. But if c is not 0, the function has to be constant for that to work. Clear? All right, let's move on. So now, what about the summation, guys? Before I even mention, guys, a derivative of summation. I want you to tell me when I set up the definition, what will I be searching for in the definition? That's very important. Okay, so this, guys, I want you to tell me, please. If I ask you to take the derivative of fx plus gx, you understand the idea is abstract. The idea is this: I have one function that I know how to differentiate separately, and I have another function that I know how to differentiate by itself. Now, what's the derivative of the sum? Tell me what expressions will I be searching for when I set it up? Because obviously, if this is my function kx, I will set it as limit where z goes to x of kz minus kx divided by z minus x. That's what I do where I don't know anything about the derivative. Right? That's one thing I can try to do. Now, what pattern am I searching for in that limit? Type in the comments. It's an abstract question, but if you cannot answer it, then you do not know what I'm searching for. What pattern or patterns am I trying to find within that limit? Again, guys, we're assuming that we know the derivative f, and we're assuming we know the derivative g. What patterns am I going to search for? All right, I'm waiting. I don't understand what intersections mean. Very simple. What pattern am I searching for? All right, let's do it together, guys. You understand, guys? If you do not know what you are trying to find, you will not find it. So I write limit as z goes to x of f of z minus f of x minus, that's one part, minus, sorry, what am I saying? Here is, so it's limit as z goes to x of fz plus gz minus fx plus gx. Z minus x. Now, what pattern am I searching for here to establish my formula? I'm searching for something that represents the derivatives of the known functions, because I'm trying to communicate new derivative in terms of old derivatives. So I'm searching for f prime and g prime. Isn't it clear? If I want a formula in terms of the derivative of the new function in terms of old functions, I need to find f prime and g prime. And how do I find them? Well, let's group them together. Look at it. So let's group like with like. So that's f of z minus f of x. I will group it together. Plus g of z minus g of x divided by z minus x. Now I can distribute it. So I get f of z minus f of x over z minus x plus g of z minus g of x divided by z minus x. And what do I get? I get f prime x plus g prime x. You understand? So what were the patterns? I was searching for f of z minus f of x over z minus x. That was the answer. Or f prime and g prime would have been fine with me. Right? It's so clear that that's what you want to find, because do you understand the goals, guys? First of all, and I'm explaining something, I wonder if you understand the goal. I am trying to learn something new from old information. I presume that I know the derivative of f and I know the derivative of g. What's the derivative of the sum? Right? You imagine it's the derivative of the first plus the derivative of the second. How do I know that? I apply the definition and I search within the definition of the derivative of the new, of the sum function, the definition of the derivative of old and the definition of the derivative of the new. Do you understand? Of both both old functions, I'm sorry. You can try doing the same later on for the minus, but you can also combine 1 and 2 together and establish this directly. Because you see, what is f minus g? F minus g is the same as f plus minus 1 times g. So you can combine the results 1 and 2 to establish the result for the difference of functions. You don't need to do more work. You can do it directly, or you can quote 1 and 2. Make sense? And this is what we have here. We were looking for the definition. So we were looking for shortcuts formulas. We now know that the derivative of a constant is 0. We know that the derivative of x to the power 5, for instance, is 5x to the 4. If we have shortcuts, we know that the derivative of sum of two functions, if I know the derivative of one and I know the derivative of the other, I know the derivative of the sum. I know the derivative of a constant times the function. You understand? So that's what I was able to establish. So for instance, You understand? What did I show? I showed, for instance, now I know how, without any extra work, how to do derivative of 5x cubed, right? Because I know how to take derivative of x cubed, it's a constant times the function. So all I do is I take the derivative of x cubed and neglect the constant for a moment, and I have this. You understand? That's by first property. So we have that. Good. And in general, by combining properties 1 and 3, I now know very quickly how to differentiate polynomials. I don't need to spend any time thinking about it. Right? So what's the derivative of this polynomial? It's the sum and differences of each piece separately. Here I kind of took the trouble of doing it slowly to show you how, in theory at least, you can quote those laws. We have the limit laws, now we have derivative laws. At least we have a few of them now. Right? And you need to, of course, if there are laws, you need to understand why they work. And so we have our shortcuts. Good? Now calculate the derivative of this quickly, guys. You see, by the way, how do you answer questions on the exam? Let's say I say calculate. Some people are so terrified of me, they go right away and go by definition. Did I say by definition? No, I did not, right? So your goal is to answer the question as it's stated, what was asked. If I say use the definition of a derivative to compute the derivative and you do it by shortcuts, I give you 0 points. You understand? You are supposed to follow instructions. Okay, so very good. A few of you answered it. Okay, that's the solution. Good. All right, guys, let's just see where you stand. So now let's see what would you say if I asked you to calculate the derivative of 2 to the power of x? Derivative of 2 to the power of x. Give me a second. Okay, Francis says something, Robert says something. When I say calculate or what can you say about it, doesn't mean that I'm forcing you to do it. I'm just saying, well, what would you say? Would you say something, right? I'm not saying, okay, so we have. You mean somewhere I made a typo? You mean in the previous question? Here? Well, here is the derivative. Let's say, so it's minus 2x. 3 times 7 is 21. You're right. But it's okay. More so, let's focus on the 2 to the x. All right. Let's see who said what. 1, 2, 3, 4, 5, 6. Okay, well, not many of you said anything. And what about the rest of you? Okay, Christiana. Zakia, not sure about 2 to the x. Okay, well, that's fine, guys. You don't have to be sure. You understand what I'm saying? It's good to be careful. Some of you are in this mindset that if a math question is asked, you have to spit some solution, no matter how ridiculous that is. It's like you are supposed to jump or do something. Wait for a second and look at it. Do we know how to differentiate such a function? Have we established a process to differentiate a function of that form? No. Do you understand what's the confusion, guys? Do you see the difference between 2 to the x and x squared, right? Here, x squared, the bottom is moving, it's changing, and the top, the head stays fixed. Here, 2 to the x means what? 2 to the x is the bottom is fixed and the head is moving. So when you answer or the derivative, when you calculate it, you are mistaking an ass or an asshole for a head. You understand? That's a pretty bad mixture. It is absolutely incorrect. And again, I try to emphasize again and again, guys, without going through the definitions, you will keep making ridiculous mistakes. Just even for simple things like that. Do you understand that to apply those questions for anything that's really interesting, you will not be able to just, it's not take the derivative of something. You have to be very, very good thinker. Let's say if you read the physics book, see how much you need to understand to be able to figure out solutions to those questions. So here is, it's completely wrong, guys. You see that this is the difference. X squared and 2 to the x, completely different functions. This is what I think when you make those mistakes, as I mentioned, of course. Let's now review exponential functions. So we have, what does it mean to say a cubed? A cubed is a times a times a. A to the power of n is a multiplied by itself n times when I have an integer power. Clear? Now, we have this addition rule for powers, which you can begin noticing this way. So if I have a to the 3 times a to the second, it means that first I multiply a by itself 3 times and then multiply the result by a multiplied by itself twice. And then you notice that altogether there are 5 multiplications of a. And that's why it's 3 plus 2. You understand? It is, I'm not going to torture you, but it's possible to establish this exponential law for any real number, x and y. But it will take, to establish it and actually know it well, will take some effort. You can try to think what happens with fractions and what do fractions mean, but it ends up being true even when the powers are not integers. Good? That's the situation. By the way, do you understand why? Let me just take that short segue. Right, so do you understand why, for example, 2 to the power of minus 3 is equal to 1 over 2 cubed? Do you understand why that's the symbol you're using? Yes, so why is that what you're using there? You see, it's really a play on this idea. Look at it. If I have a to the power of n multiplied by a to the power of m, that ends up being a to the power of n plus m. Yes? And if I have a to the n divided by a to the power of m, what happens here, right? So for instance, suppose that I have a cubed divided by a squared, right? What happens then is that it's a times a times a divided by a times a. Now, if a is not 0, I can cross away 2 of them, and I'm left with what? I'm left with a to the power of 3 minus 2. Division removes, when I divide, I remove a few of the a powers. Do you agree? Yes, a few of the a powers are removed, guys. You see, so division undoes some of the multiplication. So it's 3 minus 2. But what would happen if I had a to the power of 2 over a to the 3? What survives is a on the bottom. And you want the formula to still work. So that would be a to the power of 2 minus 3. Clear? So that's what makes that reciprocal law work. We can talk more about it if you want. So we are going to try to establish the derivative of a to the power of x, and provisionally we are going to do it. We're going to do it this way. Okay, so it's going to be much more difficult than the derivatives you've seen before, and it will take us time before we give the derivative precisely. But let's look at what happens. Okay, guys. The point is, you are trying, when you move mathematical symbols, it's not just to find the answer is 3 or 5, but to describe what are you seeing happening, what is unfolding. So unlike the previous functions, for exponentials, you will see that the second formula, the x plus h, is a better formula than the f of z minus f of x. You understand? That's the first time the second formula is very useful, much more useful than the first formula. Do you remember the differences, guys? So you have, remember, usually when I say derivative of a function at x, I might say either limit as z goes to x, fz minus fx divided by z minus x. And for all applications that we've seen so far, that was the better formula. Because if you understood what I meant, then if you use the second formula, you would have to use more symbols. No, there is another formula that it means exactly the same thing. You should know why they are equivalent. Derivative at x is limit as h goes to 0 of fx plus h minus fx over h. You understand? Those are the two formulas that they must be not just kind of, you didn't memorize any of them. It bothers me when I think about it like this. I understand why they are equivalent. I understand why they mean the same thing. Do you? Do you understand why the top formula and this formula mean the same thing, guys? No, it's not a rhetorical question, do you? Let me re-explain them. So first formula for the derivative, its limit as z goes to x, f of z minus f of x over z minus x. What are you saying? Here is the graph of a curve. Here is the point x. Here is the point f of x, right? This is one point. And then what do? You measure the slope by selecting this point. And what's the coordinate of that point? The coordinate of that point is z, f of z. Here is the secant line, right? And this point z is moved closer to x. That's what this is communicating. Isn't it easy, right? We are measuring a slope, and we are fixing the point x f of x, and we're taking z f of z as the sliding point, and we're moving it closer. Now, I can describe, that's just a matter of language. How can I describe this point? This point is close to x. Instead of doing this graph, I can say this thing. Property 2, right? So here we have that graph. Here is the point x, f of x. And I want to emphasize that the point I pick is very close to x. So it's x, but imperfect. So I can call this point x plus h, where x is the impurity. It's called perturbation. Think of it as the impurity. Understand? H is a small thing that makes it not x. So it's plus 0, 0, 0, 1, or minus 0, 0, 1, depending on the side. Clear? So if you use this and you put this point is then what? This point is f of x plus h. In this case, how do I make this point move in? I just take the limit as h goes to 0. So it's limit as h goes to 0, f of x plus h minus fx over h. Mean exactly the same thing. Yes? You understand, guys, that here is the thing. When you ask those questions, you're focused on the symbols. That's not right. Focus on the meaning. What is when you read it, what does the expression say? Understood? And if you focus on the meaning, if you can get at it, then it's very easy. What's there not to understand the second one, Francis? It says exactly the same thing. It just uses the slightly different language. It says, here I'm saying I take a point and I move it to x. And here I say, well, the point I'm taking is like x, but slightly different from it. You understand? So I just put I use a different sentence to explain exactly the same thing. So here I say, take a sliding point here, sliding point, and move it towards x. Here I say, well, the point that you're taking that's close to x, well, it's not exactly x, it's very similar to x. So it's x plus h. So z here is x plus h. I give this description. So the meaning is exactly the same. I just worded it differently, that's all. There is no question. Francis, you are seeing a question where there is no question. It's just for, you see, what we're talking about is this: my name is Arkady, and then that's one sentence, and the second is they call me Arkady. Now you're saying you cannot answer questions like this. So there's no question here. I'm just saying the same thing in two different ways, or I can say it in how many ways I like. There's no question at all. But the way you speak can actually affect the assumptions psychologically that you can make, the ideas that you can reach. So back to this process, guys. Do you understand what I'm saying, guys? So you have two definitions of the derivative. They mean exactly the same thing. They're just different wordings of exactly the same thing. Now, the second wording actually ends up being better. You understand, guys? If you study law or you go anywhere, right, the way you word things does have an effect. You can word something in a way to offend a person, and you can word the same thing as to get the person to take your point. You can, and also some particular wordings might inspire you to come to a particular conclusion. Another wording will inspire you to come to a very different conclusion. Wording is important, even if the essence communicated is the same. So here I'm going to try to go by the definition of the derivative using the second formula for a to the x. Are you ready? So I write f of x plus h minus f of x over h. And the reason I use that formula, look at it, guys. Let's see if you can get it. So it's limit as h goes to 0. It's ax plus h minus a to the x divided by h. Are you so far with me? Now, because it's an exponential function, I have this property. If I have this side, I can factor it out. So I can write ax plus h as ax, ah. And that allows me to factor out a to the power of x. I factor it out, and I'm left with this limit. Yes? Now let's see if you can interpret what just happened here, guys. Not to solve. You see, you right away think, what's the answer? What does it say about this function? What does it say about this function? Look at it again. Look what we did here, guys. So the function is some a to the power of x, where a is bigger than 0. So what you have is I take the derivative of this function at some point x, and and that's limit as h goes to 0 of ax plus h minus ax divided by h. Then my next step was to break it apart. So it's limit as h goes to 0, ax ah minus a to the x divided by h. Good? This step, everybody is with me. Yes, guys? Are you with me? Yes. You have to be really with me because I'm going to ask you a question. Gabi sind Sie bei mir? Are you with me, guys? Do you see what happened here? Now, Francis, how do I factor it out? So this is limit as h goes to 0 over h. And I can write a to the x, ah minus 1. Good. Do you understand so far? And I factor it out. Because look at it, the limit is only interested in h. Limit as h goes to 0. And what do I see here, guys? I see this, ah minus 1 over h. Now, I'm asking you this very important question. That's why we train it. Guys, what do I see? In terms of the function, what am I seeing? Let me give you a hint. I was taking the derivative at the point 0, sorry, at the point x. Where am I? What am I doing now? What is this limit? Not what does it equal to, guys. That you see, you always think what equals to, but what is the limit? Why is it 0, Francis? If it were 0, then the derivative of a to the x is 0. That's impossible. What is that limit? Not symbolically. What is it about? You understand what I'm asking, guys? So I was going somewhere and it was dark. And then I heard, yeah, right? What was this thing that I heard? Can you answer that question? Or if you don't recognize it, I was walking somewhere in the dark, and then I hear moo, right? Where am I located? I am where? Forest? I mean, I'm not sure. Maybe I'm in the forest. Farm. Here you go, guys. Look how quickly you figure out that I'm in a farm. Because I was hearing moo, right? I'm in the farm. So you should understand the same. That's what I'm asking you. Understand it? You're right away thinking the answer is 5. It's okay. That's not at all how you do mathematics. What am I staring at? I was taking the derivative at x. Now I do this process. What am I staring at in the limit? Well, it's not 0 over h. 0 over h, Francis, is 0. What am I staring at? Right? You don't need to give me the name of that particular cow, but tell me what is the cow. What is the cow? I don't want to know if it's Bessie, right? I don't want to know if the answer is 7 or 2 or not. I'm asking you, what is it? What sort of creature is it? Is it a cow? If it's so, what is that cow? Is it a cow? Is it a lion? Is it a what? You see? It has to be the same thing that happens in your mind when I say moo, you right away know what I'm talking about. You have to know what I'm talking about. Definition of the derivative at x equals 0. Christiana understood me. It is the definition of the derivative at 0. Understand? Let's look at it again. Look at it carefully, guys. Look at this formula. What is that formula? That formula is a0 plus h minus a to the power of 0. Remember that any non-zero number to the power of 0 is 1. divided by h. That's the definition of the derivative of this function. This is just simply f prime at 0. Do you understand? I started taking the derivative at some point x, and I end up realizing I need to take the derivative at the point 0. No other point is important, only the point 0. You understand? Christina got it. The rest of you understand what I'm saying, guys. It's what I mean by recognition. That you have to really think about what you are seeing, not just if the answer is 2 or 7, that's meaningless even if you are correct. What are you watching? Here again, guys, this is the derivative at 0. So that means that the derivative of my function is the function itself multiplied by the derivative of the function at 0 by a constant. Do you understand what that means? That means something like this. That means that, that the derivative of a to the power of x is maybe, I'll just make a number, 5a to the x. Or maybe 3.1 a to the x. Or in general, some scalar times a to the x. It's not very different from the original function. That's what that means. I did not solve that derivative, but I know that the derivative is not very different from the original function. Do you understand? That's how that's how you're thinking. You see, it's not that you get the answer. You actually, it's a very difficult limit to calculate directly. We're kind of bypassing it. We're just trying to understand what this is saying about the derivative. It says that the derivative is not very different if it exists. I need the derivative at 0. That's all I need for it to exist. And if the derivative at 0 exists, the derivative is not very different from the original function. It's not changing the function too much. Do you understand what I'm saying, guys, right? So it's a qualitative result, not a numeric result right now, a qualitative result that I realize something about the function, some sort of quality it has. It's a very important quality. Are you with me? This is, again, guys, look what I have done there. So that means that if I say the derivative symbolically is f prime of 0, because I haven't figured out to calculate that limit, I just say symbolically the answer is f prime of 0. You understand? Symbolically, that constant is the derivative at 0. That's what I just noticed. So what happens, I can now take many derivatives. Take derivative once. All you have to do is multiply the function by f prime of 0. Take the derivative again. The derivative moves through the scalar. It's going to be f prime of 0 squared times f of x, and then f prime 0 cubed times f of x. Do you understand? Are you with me, guys, or do I need to say more about it to confirm in the message? Come on, I want to see more of you participate, guys. You're sitting there with looking at me or not looking at me. Do you understand what happens? Or do you need more explanation? Well, we're going with more explanation there, but are you with me up to this point, guys? Do you see what I did? I just recognized that I was taking derivative at an arbitrary point x, and I ended up taking the derivative at the point 0. This limit here, this limit is the derivative of the function a to the x, where x equals to 0. Do you all see that? That's the first part, guys. Do you all see why? Because it has that form. Look at it, right? I just wrote, what is this? This is the same as a to the 0 plus h minus a to the 0 divided by h, which is the definition of the derivative at 0. Do you all see that? And instead of bothering to solve the question, I drop it because it's a very difficult limit. Instead of bothering to solve it, I say, okay, it's going to be some number. And that number I will label as f prime of 0. Because the function is f of x equal to a to the x, I'll label it as f prime of 0 to just observe the qualitative behavior of my function. I do not know what that number is yet. You understand? It's too difficult for me to figure out what the number is. I am going to try to develop techniques later. I'm just saying, okay, it's some scalar. Well, so when I take the derivative of a to the x, it will be some number multiplying a to the x. Good? Could that, let me actually draw a graph for you and ask you, let's say there's something like this. This is the graph of 2 to the x. Could the number multiplying 2 to the x when I take the derivative be equal to 0? Could that be the number? Could 0 be the number? Okay, and if you say, okay, so Humira says no, Christiana says no. What about the rest of you guys? You understand what I'm asking? I'm just a qualitative example. We know that the derivative of 2 to the x is going to be some number times 2 to the x. That's what this result proves. Clear? Could that number be 0? Okay, maybe more than 0, but right now not 0, right? Right now we can be sure that it's not 0. Do you know why I can be sure it's not 0? Because this curve is not a constant. If it would be 0 times 2x, then that means that the derivative is 0. But the derivative of a non-constant curve, of a non-horizontal line, cannot be 0. So that constant cannot possibly be 0. Do you understand how I reason? It could be maybe very close to it, who knows? Maybe it's a number close to 0, but cannot ever possibly be 0. Because that will mean that the curve is a horizontal line, which it is not. And you don't even need a graph, because you know 2 to the 1 is 2, 2 to the 2 is 4, so it's not a horizontal line. Right? Wonderful. So you are with me, I hope. So this is the derivative as far as I know. It's a to the x times some unknown number, which happens to be the derivative at 0. Unknown because I haven't figured out how to solve it yet. Good? Now, because we have technology, we have electronics. Okay, first, before we actually have electronics, you understand if I continue taking derivatives by using the fact that I can move the derivative past the scalar, do you all see that I will get this situation? Derivative of a to the x, I get 1 copy of f prime 0. Take the derivative again, I get an extra copy of f prime 0. Do you see that? Let me just illustrate one step in case somehow you don't. Look at it. Derivative of a to the of from here to here, I can just take f prime of 0 times the derivative of a to the x, and what happens? It's f prime of 0. Here we have f prime of 0 a to the x. Right? That's why we have square. Yes? Now we can try to use a calculator. It's not a fair way to do that, but just to get a sense of what that number might be, let's use a calculator. Ready? We cannot use truly a calculator because you don't know what a calculator is doing. You understand? And actually, there are some examples where the calculator can give you a mistaken answer. That's not true. Right? So here is what I imagine. Okay, what is that number going to look like? H is going to 0. Right, which means it should be what? 2 to the power of a number close to 0 minus 1 divided by that same number. So when I take limit, instead of taking a limit, I say, oh, the result is going to be good enough if it's this number, if it's 1 over 1,000. I arbitrarily selected 1 over 1,000. Do you understand? I just zoom in somewhere near 0, and I'm trying to measure this. You see what I'm trying to do is near 0, I'm beginning to zoom in. Look at it, I'm zooming in near 0. And you see that it becomes a straight line? on the graph, I'm trying to measure the slope of that line. What is the slope of that line? And I use a calculator to do that. So I think that, look at it, I think, okay, well, if the difference is, here actually it already looks like a line, even though the difference is like 1/10 or something, right? Not even 1/1000. So I zoom in until I see something like this. Look at it. You see 0.01, right? And I continue 0.005. Here, you see this? This is my 001. So I'm using this point to estimate this point and this point to estimate the slope. Very close. You agree? So I plug it in the calculator, and what I get is approximately 0.69. So it's not a precise result, but it seems to me then that the derivative of 2 to the x is approximately 0.69 multiplied by 2 to the x. That number that was not known to me is approximately 0.69. Are you clear? I did not understand because I don't know how a calculator did this calculation. I mean, I'm just hoping the calculator did not lie to me, and that's a good estimate. So we're going to replace it later on. But right now, I just wanted to give you a sense of what that number might be like. Are you clear? That's good. I hope you are, guys. So now let's see how clear you are. Do you have a calculator with you, or you have a computer, right? So what you're going to do, to the best of your ability, you're going to tell me what is the derivative of 3 to the power of x. You understand? I'll write it on a separate sheet. I want you to give me this experimental result, and to the best of your ability, tell me what will be the derivative of 3 to the power of x. Do it through all the process, from the beginning. Good? The full process, and give me an estimate. Okay, a few of you give me the constant. Christiana, Tzvi, I'm very happy about it, but I see similar people participate. I want to see somebody new. Come on, guys. All of you should give me the answer. All of you are making the discovery of what's the derivative of 3 to the power of x. It's exciting almost, right? Okay, that's the constant, but you can give me the full derivative. So derivative of 3 to the x is what? Exactly, David, probably approximately that, okay? I'll wait 1 more minute and we do it together. Okay, Jet, thank you. All right, let's do it together, guys. Here is 3 to the x, right? So first of all, I mean, we already know that all I need to do is find the limit at 0, right? Because if I take the derivative of 3 to the x at arbitrary x, it suffices to know what's the derivative at 0 based on the calculation for a general a. You understand? I mean, I don't need to repeat it, do I? You understand why I have to focus at 0 specifically? It's just what the limit tells me to do. So here is what happens. Derivative of 3 to the x is approximately, first I need to do that quantity, 3 to the h minus 1 over h. So I put an approximation to something close to 0, and I get 1.099. And I'm hoping, again, guys, it's a terrible, it's provisional. You understand? I mean, first of all, the calculator gives you that answer. If you don't understand what the calculator did, you cannot trust that calculator, even if you think it was well designed. You can actually create situations where a calculator will give you the wrong answer. Okay? So the answer is about 1.099 times 3 to the x. It's by no means like you initially supposed. The derivative is by no means x times 3 to the x minus 1. Do you agree? You understand? Which would never occur to you because you right away realize it's not x cubed, it's not the same way. So why should the derivative be the same? Follow the same pattern. And then I look at the definition and I say, oh, of course it will not follow the same pattern. Even if I cannot solve. You understand the difference, guys? I did not find the actual derivative at 0. I did not solve that limit yet. It's a difficult limit. I just interpreted what it would mean to solve that limit. And I get a provisional result. We will improve on it later on. We will give a precise result because you see, this is not precise. How good is the approximation and what was done? There's a lot of problems here. Do you agree? I mean, first of all, you allowed some calculation that you don't understand to be carried by a calculator. Secondly, it's not a precise result. Right? And then look what happens, guys. Look what happened first. We got a number less than 1. Secondly, we got a number more than 1. Okay, Gabi, take care. Two to the power of 8. You understand, guys, what I'm saying? Derivative at 3 to the x. The constant multiplying 3 to the x was bigger than 1. For 2 to the x, it was smaller than 1. Let's try 2 to the 8. 2 to the 8, if we do that thing, we get a number even closer to 1. Are you with me? Now my question is, guys, if you had to choose among different a's, you see some a's seem to give you a constant more than 1, some seem to give you less than 1. What would be your ideal a? What would you want? Wishful thinking. F prime of 0 in a to the x, f prime of 0, a to the x to b. You understand my question? Now you have results that are appearing, but what would you have liked this result to have been? Humira says this. Wishful thinking, guys. What would you want? Right, so you want this to be equal to a to the x, right? We have the derivative is almost the original function, not quite, there is something multiplying it, but we would like to have it exactly the original function because then it's not hard to carry the calculations. You understand? You understand how I develop it, guys? I see that when I take the derivative of exponential functions, I get a constant multiplying the exponential function. Now, it's not nice to multiply by the constant unless the constant equals to 1. It cannot equal 0. That's impossible, right? So the next simple constant is 1 for multiplication. And that's what we do, guys. So this is our definition. We hope, it's not even a definition yet, guys, right? We postulate the existence of some number e. You play around, guys, between 2 and 3. You see that if you play around with your calculator, you can get it a bit better and better to closer and closer to 1, that constant. So you postulate that there will exist a number e, which lies between 2 and 3. And for that number, if you were to carry this calculation, you will get 1. Notice it's a hypothesis. We don't know that this thing exists because we have many things that we're unaware of. We will later on try to explain what e is. But right now, we just postulate the existence of the exponential function, which we call e to the x. Right? We want we are postulating that there will be a base e. It's a number between 2 and 3 where the derivative is simply e to the x, because the limit here is 1. The derivative of this function at 0 is 1. Clear? All right, let's move on. This is the next stage of our process, guys. So you do understand about exponential functions, right? So you understand what we have done in our calculation, how we derived anything. Yes? Very simple if you think about it. We use the second notation because we use the exponent addition law, right? And we were able to extract some qualitative information that the derivative of an exponential function seems to be the exponential function multiplied by a constant, and that constant happens to be the derivative of the function at 0, if it exists. There are lots of ifs we haven't justified, right? Since we haven't calculated the limit, maybe the limit does not exist. Good. And we played around with a bunch of limits, and we see we can get numbers closer to 1 by adjusting the number between 2 and 3. Good. And we just answered that the simplest expression would have been if it's 1, and the hypothesis is that there would be a number that works. And that number is between 2 and 3. Now, again, guys, I would like to emphasize what we have done when we carried out the calculation for 3 to the h minus 1 over h. When we made this approximation, we assumed that the limit will converge, and we don't know that. And secondly, we used estimates of numbers like 2 to the power of 0, 0, 1, or 3 to the power of 0, 0, 1. And we do not know even how to calculate the root of 2. I mean, if I didn't give you a calculator, would you be able to calculate root of 2? And here you're asked to compute the 1,000th root of 2 or the 1,000th root of 3. How do you do that? Do you understand, by the way, why that notation works? Let me just also segue and mention that notation. Guys, y is a to the power 1/2 the same as root of a. Would anybody care to explain? Root of a means find a number that when multiplied by itself gives you a. Why do we use the notation to the power of 1/2? Why is it the same thing? Why use the notation 1 over 2? You see, let me give you a very quick explanation what happens here. Guys, what happens if I take a to the power of 3 and I square it? What happens if I square it? So that means that it's a to the 3. It means a to the 3 times a to the 3. You agree? So altogether it is a to the 6. So it's 2 times 3. Do you agree? Or 3 times 2, however you like calling it. Good? So you have this, if you think about this pattern, you see that a to the power of n to the power of m, that would be a to the power of m n. Yes? Now, when you're trying to represent root of a, so let's say I'm going to say root of a is a to the x. Or let's not use x so you're not confused by that symbol. Let's use a to the power of t. And t is supposed to represent root a. Now, what is root a? I know that means that a to the power of t squared is supposed to be root of a squared, which is supposed to be a. In other words, a to the power 1. You understand? But what is a to the t squared? That's a to the 2t equal to a to the 1. So you get that 2t is equal to 1. And so your notation is t equal to 1/2. As simple as that. Clear? It's not arbitrary, guys. If you understand what you're trying to communicate, it's not arbitrary which symbols you use. That's why a to the 1/2 is supposed to represent root. A to the 1/3 is supposed to represent cube root. Clear? Wonderful. Okay. So actual calculation of root 2 or root 3 or any roots, I mean, you see the fact that you're not able to produce a procedure, I'm sure. How many of you, if I told you without a calculator, tell me what's the square root of 2, how many of you would be able to carry out a procedure? No, right? I will teach you how to do that. In fact, if you think a little bit, you can generate a process that will give you root 2. You see, if you're just a bit imaginative, there are many ways to do that. So here is the question that I have here, guys, right? So do you see the difference between the symbol root of x as opposed to 1 plus x squared? What's the difference between those two functions? Well, in one function, you don't really have a formula. When I say root of x, you don't have a formula for carrying the calculation. The fact that I write this symbol on top of x doesn't tell me how to calculate it, right? In other words, for instance, here is the situation. Let's say here is the function f of x, and here is the function g of x, right? So if I tell you calculate what is f of 2, well, you say 1 plus 2 squared, which is 5, right? You calculate easily. But now I tell you calculate g of 2, and you don't know what to do, because you don't see what is it that you're supposed to do. What process are you supposed to carry the calculation? What formula you have for it, right? 1 plus x squared gives you a formula. It says take the number, multiply it by itself, add 1. So we know how to do multiplication, we know how to do addition, we know very little else. Good. And so we are, you see, this is an example of a polynomial function. For polynomial functions, we can carry calculations explicitly. Yes? So my question is the function e to the power of x a polynomial? Or any of the exponential functions, could they be a polynomial? It's a very important question, right? Let's begin with e to the x. Could it be a polynomial? You understand why I'm asking? I mean, you might think e to the x, it has a formula, right? So, I mean, if I know the number e, maybe if you tell me e squared, it's just e times e, right? It only uses multiplication. But what about e to the power of 1/2? That would be root of e. How do I do that process? You understand? So I'm asking, is there could I come up with a formula for e to the x, a polynomial formula that will allow me to carry out calculations? Yes or no? And let's try to think about it. So a bunch of you say no, but can you justify if it's no? Or can you justify if it is yes? Now, what's true about e to the x? I don't even know what the base e is to carry out a calculation. I just say it's a hypothetical number between 2 and 3, right? So this is a function. So e to the x is a function that satisfies several things. What's the derivative of that function? The derivative of that function is the function itself. Yes? And there is only one value at which it's easy to evaluate. I know that f of 0 equals to 1. Yes, it's true. No quadratic polynomial equals its derivative, Christiana. That's already you're on the right track. You see, do you understand, guys, that why a number to the power of 0 equals to 1? It's like this. If I have, let's say, 3 to the 0, it's like 3 to the power of 1 minus 1, which is like 3 divided by 3. 3 to the 1 divided by 1, which is 1. That's why the power of 0 gives us 1. Do you understand that, guys? It's not arbitrary. The number to the power of 0 is 1 because it means that there were equal match of multiplication by the same number in the denominator and numerator. And they cancel out to 1. Clear? Now, again, I'm asking you guys, could a function like this be a polynomial? No, Christina, you say no. Now you say no, then why no? You have to, if you're saying no, there must be something about polynomials that's very different as opposed to this function. That's a meaningless phrase. No, because it's an exponential function. You understand that exponential functions is not really, you don't even know what it does. Right? There are lots of problems in this development. First of all, we haven't developed what it means to exponentiate. You might know what it means to exponentiate to the power 2, 3, 4, but if you look at it deeply, you don't understand what is to exponentiate to the power of pi, or to the power of 1/2, or to many other numbers. Right? So there is the issue of that not being clear what is it that we're doing. But even if it is clear what we're doing, why not be able to come up with a different formula that produces the same thing? Polynomial formula that only uses multiplication and addition. Is the question clear to you guys? Even if you don't know how to answer it, is it clear to you what I'm asking? Should be very clear, guys. I'm asking, can you come up with a calculation? Can you come up with a process that will carry, using addition and multiplication, carry the computation? So for root, you don't know how to calculate root of 2. That means that you don't have a process to carry out that calculation, a mechanical process. In other words, you don't have to think, but you just kind of plug, number, multiply, add, that type of thing. Okay, so I'm asking, can you come up with a mechanical process using only addition and multiplication to simulate exponential functions, simulate e to the x? In particular, simulate a function whose derivative does not change the function, and a function at 0 equals to 1. You see here, I try to explain to you what goes wrong. So, I mean, first of all, if we have e to the 3 power, it seems to be involving multiplication of the same number 3 times. But if I have 1/2, I do not know how to carry out the calculation. And also, if I select different powers, it's carrying multiplication different number of times. A polynomial function uses the same number of multiplications and additions each time it calculates. You agree? So I always use the same number of multiplication processes, the same number of addition processes and whatnot when I carry out the calculation. Well, I mean, the raised, that's just appearance wise. I don't know what it means to be raised to a fraction or negative powers, Kumira. Right? There is a problem there that there is also an assumption that you know what it means to raise to a negative or fractional power. Right? Those are just symbols. How do you carry out calculation? So here is one suggestion, guys. Let's try. Let's say, ask ourselves, could it be a quadratic polynomial? In other words, where I don't use more than square. This means quadratic or less, you see, because I can make a to 0. Can it be a polynomial that's quadratic? Well, let's see. We know one thing about this function. We know that if I take derivatives of it, it's not going to change. But if I take derivative of polynomials, I know how to do that. Look at it. I take one derivative, and the degree decreases. I take two derivatives, the degree, it becomes a constant. Take three derivatives, it's 0. So quadratic functions after three derivatives vanish to 0. But the exponential function after three derivatives, e to the x, remains the same. You understand? So they cannot be the same function. No quadratic can simulate exponential function, because take derivatives of quadratics, they disappear. Take derivatives of exponentials, they don't change the exponential. No degree, but we don't know what it is. I'm asking you very challenging things, guys. Yeah, I mean, I'm confusing you in some sense, because your grasp of all those concepts was very tenuous, right? You memorized exponential powers, you memorized this, you memorized that, and because you memorized, they are kind of they're in your shelves, very accurate. Here is the polynomial, here is the algebraic functions, right? You imagine that you can place them on different shelves, but if you consider it, can you? Are they not the same shelf? That's the question I'm asking. Right? In fact, what did you place on the shelf? You just created a symbol, but what does this symbol do? How do you calculate? So here I'm showing you that an exponential function cannot be a quadratic. You understand why? Because I actually know my objects on the shelf well enough. I see, oh, the quadratic functions, three derivatives make them disappear. But the exponential function, we just verified, derivatives don't make them disappear. They, as they say in Russian, как с гуся вода, like water from a pheasant's feather, doesn't stick. Yes, exactly. It has a slope, which is itself. The slope of the function is the y coordinate of the function. So what does it mean, guys? The derivative of e to the x equal to e to the x, it means that the slope is always the y coordinate. Remember, we spoke about the x coordinate. Let's say derivative of x squared is 2 times x. That means derivative is always twice the x coordinate of the point you zoom in. Now, the slope of an exponential function e to the x, if it even exists, right? It is the y coordinate, always the y coordinate of where you're zooming in. Do you understand? So if I zoom in at the point 0, it's e to the 0, so it's 1. The y coordinate is 1. And the slope is 1 and 0. If I zoom somewhere else, it would be a different slope, but it's always the y coordinate. Are you with me? Make me worried, you know, guys. So you understood why it's not a quadratic. If you understood why it's not a quadratic, maybe tell me one last thing. Can it be a cubic? Can it be a degree 3 polynomial? And of course, why not? Why or why not? Could it be degree 3? At the end, we have derivative equal to 0. What's the end? If you take derivative of degree 3, it becomes degree 2. Notice, right? Each power drops. Derivative of that becomes degree 1. Derivative of that becomes constant. Derivative of that is 0. After 4 derivatives, cubic disappears to 0. But e to the x never disappears. Yes? Can it be degree 4 polynomial? No, right? After 5 derivatives, it disappears. Good? So is it a polynomial, guys? Can it be degree million polynomials? Can e to the x be simulated by degree million polynomial? The answer is no, because after 1,000,001 derivatives, that polynomial disappears to 0, but my e to the x remains e to the x. Do you understand? So it must be a function that is different from every polynomial. But notice every finite polynomial. You see, I mean, if you're very imaginative, you say, okay, I cannot achieve it if I make a finite polynomial. In other words, where I have x, 0, no x, x1, x2, x3, right? But what if I make an infinite polynomial? And that will be what we talk about next class. Good? All right, guys, you had a long day. I will stop recording.